Intermolecular forces are forces between molecules. We do care about them because they affect the melting point, the boiling point, and the solubility of molecules. Functional groups, they determine the type and the strength of the intermolecular forces. There are different types of intermolecular forces. The strongest is an intermolecular force that occurs between two ions. The ions can be either atoms or they can be polyatoms. So this is an example of sodium chloride. Sodium is positive, chlorine is negative. Charges should balance each other. The type of bond is an ionic bond. This is an interaction and it is not a bond. It's an electrostatic interaction in this case. This is an example where the negative ion is a polyatom, and this is an example where the positive ion is a polyatom. Covalent compounds, they do have intermolecular forces. Their intermolecular forces is weaker than the ion-ion dipole interaction that exists between ionic compounds. An example of intermolecular forces in covalent compounds is London forces or the van der Waals forces. These are the weakest type of intermolecular forces, and they occur between any two compounds that come close to each other. So that they won't repel each other, they will create a temporary dipole, and this temporary dipole will attract the molecules together. We care about van der Waals forces whenever we have two nonpolar molecules coming close to each other, because if they are nonpolar, this is the only type of intermolecular force that is going to happen between those two molecules in there. By definition, van der Waals forces depends on the electron density of the molecule. So let's say, for example, here I have a chain of 5 carbons. The carbons are represented by a black circle, and the hydrogens are represented by the white circles. Okay, so here I have a chain of 1, 2, 3, 4, and 5 carbons. It's called pentane. This is the condensed form of pentane. I have two pentane molecules that are close to each other. When they come close to each other, these two are nonpolar molecules. When they come close to each other so that they won't repel each other, they create a temporary dipole due to their electron density. So, and as you can see, the electrons or the electron density is spread over a larger surface area in here so that the interaction will be stronger. So if I have a chain that has no branches coming off it, then this means that the interaction is going to be stronger because the surface area of the molecule is larger. Compared, for example, to another two molecules with the same number of carbons, same number of hydrogens, but now they are branched. See, I have here a carbon and 4 carbons around it. I'm still dealing with 5 carbons in there, but now the molecule is kind of like a compact molecule. So if it is a compact molecule, then the density in there, the electron density, is going to be smaller because the surface area is smaller. So the attraction is going to be weaker. So as the surface area becomes larger, no branching, as the van der Waals forces increase. But still, the van der Waals forces are the weakest type of intermolecular forces. For molecules that have halogens, whether the halogens are dihalides, like two fluorines coming together or two iones coming together, or whether they are alkyl halides, like RXs, RCLs, RBRs coming together, we still are dealing with the same electronic cloud, but instead of naming it van der Waals forces, because now the electronic cloud is going to depend on the size of the halogen and how close the electrons are to the nucleus, then we're going to call the van der Waals forces polarizability whenever we are working with those halogens in there. So, by definition, polarizability is the electronic cloud around the electronegative element. And the polarizability normally exists between nonpolar diatoms. So if you have a diatom, two diatoms that are coming close to each other, we know that F2 is nonpolar, right? Um, Alkyl halides, they are nonpolar as well. So whenever you have those dihalides or alkyl halides coming close to each other in there, the halogen is going to create an electronic cloud. And that electronic cloud depends on the size of the halogen. For example, iodine is larger in size, so they have bigger electronic cloud than the fluorines. So the type or the interaction, the forces of interaction between two iodine molecules whenever they come together is higher. So the polarizability is higher than whenever two fluorines come together. So if we have two alkyl halides, like two CH3Is next to each other, or two CH3Fs next to each other, and you're asked which one has a stronger intermolecular force, you have to look at the size of the ion in there. Iodine again is larger in size. They do have a bigger electronic cloud. The electrons are loosely held in there. That is going to make the forces of attraction between two CH3I molecules to be stronger than that between two CH3F molecules in there, because the iodine will be more polarizable. Ion dipole interaction is another example of intermolecular force that exists for covalent bonds. Now, this one is going to be stronger than the van der Waals force. It exists between an ion and a molecule that has a dipole. Let's say, for example, you want to dissolve sodium chloride in water. So when you want to dissolve sodium chloride in water, chlorine is negative, so the chlorine is going to come around the water and is going to interact electrostatically with the hydrogen. On the other end, sodium is going to interact with the oxygen. So this is why sodium chloride is dissolved in water, because sodium chloride makes an ion dipole intermolecular force with water. Another type of intermolecular forces in covalent bonds is the dipole-dipole interaction. This one is formed when you have difference in electronegativity. And the difference in electronegativity is enough to form a direction of polarization. Carbon has a certain electronegativity value. Oxygen is a higher electronegativity value than carbon. So this is why the direction of polarization is towards the oxygen. This is your direction of polarization in there. So let's say, for example, if you have a solution of aldehyde molecules in there, these aldehyde molecules will arrange themselves in a way so that the negative end of one molecule is going to interact with the positive end of the other molecule. This is the dipole-dipole interaction, so that they will not repel each other. Now, the dipole-dipole interaction is a weaker intermolecular force than the ion dipole interaction. So if we want to compare so far, London forces are the weakest, then the dipole-dipole interaction, and then the ion dipole interaction. The ion dipole interaction is the strongest among all of those types of intermolecular forces. Hydrogen bonding is the strongest type of intermolecular forces between covalent compounds, and it happens between two molecules. One molecule should have a hydrogen connected to an electronegative element, and that hydrogen of that molecule should interact with an electronegative element. Both electronegative elements can be either an oxygen, nitrogen, or fluorine. So if you have two methanol molecules, they are in solution, they will exhibit hydrogen bonding because the hydrogen bonding will be between the hydrogen in one methanol and the oxygen in the other. Here we do have two hydrogen bondings in there, two times the hydrogen bonding. On the other hand, if we have, let's say, if we have a ketone in there, so if we have two molecules of ketones next to each other, so this is acetone, this is the simplest form of a ketone. If we have two acetones placed next to each other, they will not have hydrogen bonding because none of them has a hydrogen connected to an electronegative element. However, acetone can do hydrogen bonding with water because the conditions here, you do have a hydrogen connected to an electronegative element, and this hydrogen will interact with an electronegative element. So we can say that acetone is water soluble because it can do hydrogen bonding with water. Solubility is when a solute is dissolved in a solvent or when two solutions are miscible with each other. And the rule for solubility is like dissolves like, meaning that if you want to dissolve a nonpolar compound, then you have to choose a nonpolar solvent. And same thing for the polar compound, you have to choose a polar solvent. Any hydrocarbon that is made up of carbons and hydrogens, whether it's an alkane, alkene, alkyne, benzene, no matter how many carbons these hydrocarbons are, one carbon, two carbon, three carbons, all of those are considered to be water insoluble. Alkyl halides also they are water insoluble. Although alkyl halides they have a polar bond, and the polar bond is between the carbon and the halogen. So this is a polar bond, but um, alkyl halides are considered to be non-polar molecules because of their carbon chain. So alkyl halides, no matter how many carbons they have, even if they have one carbon, they are water insoluble as well. Now, the rest of the functional groups, these are water soluble, but up to, of course, five carbons or less. More than five carbons, even though they do hydrogen bonding, they are not water soluble. Let's have an example. Alcohol. Alcohols, they are soluble up to five carbons. More than five carbons, they are not water soluble. So if I have an alcohol of a three carbon chain and I want to dissolve it in water, alcohols, they do hydrogen bonding with water. They do hydrogen bonding. The hydrogen of the alcohol bonds with the oxygen of the water, and the oxygen of the alcohol, they do hydrogen bonding with the water as well. Um, Now, if I increase the number of carbons in the alcohol, let's say if I do seven carbons in the alcohol, even though I have hydrogen bonding, I will not have my alcohol dissolved in water because of the chain of the carbons, because hydrocarbons are water insoluble. Aldehydes, they are water soluble as well. And again, we are talking about aldehydes of five carbons or less. Okay. Here I have an example of an aldehyde that is seven carbons, and see how long the carbonate chain is. This carbonate chain is going to prevent that aldehyde to be water soluble. The end is going to interact with the water. So you're going to have an interaction, you're going to have hydrogen bonding with water, but the tail of the aldehyde is going to be hydrophobic, meaning that it's not gonna like to be attracted with the water, it's gonna repel the water. So this is why this aldehyde is not gonna be water soluble. Let's say if I have two aldehydes and two ketones, will these compounds hydrogen bond with themselves? The answer is no, they won't, because none of them has a hydrogen next to an electronegative element. Aldehyde has a hydrogen, but the hydrogen is next to the carbon. It's not next to the electronegative element. So these two, they don't do any hydrogen bonding with each other. Same thing if I have two molecules of this ketone in there, even though the ketone here is water soluble because it can do hydrogen bonding with the water, but it cannot do hydrogen bonding with itself. Butane, for example, is a nonpolar molecule. So it needs to dissolve in a nonpolar solvent like carbon tetrachloride. It does not do hydrogen bonding with water. So this is why it's not soluble in water. Acetone, on the other end, is made up of three carbons. So this is a small carbonate chain. It makes hydrogen bonding with the water because it does have a dipole between the carbon and the oxygen, and it does have a direction of polarization. So it is a polar molecule from the carbon double bond O. So this is why it is water soluble. It is not soluble in carbon tetrachloride because carbon tetrachloride is a non-polar solvent that cannot dissolve a polar molecule. The boiling point and the melting points are affected by hydrogen bonding. So, boiling point by definition is the temperature where the liquid changes to gas. And the stronger the intermolecular forces, the higher is the boiling point. So we expect that compounds that have hydrogen bonding, they should have the highest boiling point. Like let's say, for example, we are comparing between an alkane, an aldehyde, and an alcohol. Alkane only has van der Waals forces. The aldehydes, on the other end, because they do have a dipole between the carbonyl and the oxygen. This is the only polar bond in the aldehyde. It's the carbon and the oxygen. This is the dipole creating two charges, creating a partial positive charge here on the carbon and a partial negative charge on the oxygen. So aldehydes, they do have van der Waals forces and they have a dipole-dipole interaction as well. Now, aldehydes here has no hydrogen bonding between themselves. They hydrogen bond with water, but they do not hydrogen bond between themselves. On the other hand, alcohols, they have van der Waals forces. So as we said, van der Waals forces, they exist between all molecules in there because of the electron density. They have the dipole-dipole interaction, and they do have the hydrogen bonding. If you place two alcohol molecules next to each other, you will have hydrogen bonding interactions in there. So the higher the intermolecular forces, here you have three types of intermolecular forces for the alcohols, and one of them is the hydrogen bonding, which is the strongest. That is going to increase the boiling point. So you can see the boiling point of the alcohol is the higher among all of them. For compounds that have a similar functional group, here I'm comparing between two ketones, you have to look at the carbon chain. So the more carbons in the chain, the larger the surface area. And as the surface area increases, as the interaction is going to increase. So the boiling point is going to increase. For compounds that have different halogens in there, you have to look at the size of the halogen. And as the halogen is bigger in size, this makes it more polarizable because the electronic cloud around it is distributed over a larger surface area. So that is going to increase the boiling point. Melting point is the temperature where the solid changes into a liquid. It depends on the energy it takes to overcome the forces between the molecules or the intermolecular forces that are holding them in lattice. The stronger the intermolecular forces, the more energy is required, so the higher is the melting point. This is why molecules that have hydrogen bonding, they have higher melting point than molecules that have van der Waals forces. For compounds that have the same functional group, here I'm comparing between two alkanes. They do have the same number of carbons as well. It takes more energy to melt a compact molecule with a smaller surface area than a molecule that has a larger surface area with the same number of carbons. Soaps are salts of esters. We call them salts because um, one part of the soap is made up of an ionic interaction between the oxygen and the sodium. This is a hydrophilic head and it is a must for the structure of the soap. This is the water soluble part. We have a water non soluble part or insoluble part, and that is made up of more than 14 carbons. It's a long carbon chain. This carbon chain does not like water, it repels water. This is why we call it a hydrophobic part.